SGP Graduate School. My name is Amit Bermano. I'm from Tel Aviv University, and today I'd like to talk to you about fabrication-aware design. Now, before I start, I just want to say that a lot of my slides are taken from this course given at MIT by Wojtek Matusik and David Levine. There's also a SIGGRAPH course from last year that is also given by Wojtek Matusik and Adriana Schultz. If you really like this field, I really recommend going into these courses, looking at more material. Anyway, we can get started. Whether you are aware or not, according to analysts, we are in the midst of the third industrial revolution. The first industrial revolution was about centralizing production, where we moved from having small huts or workshops that produce a product from top to bottom to factories where everything was more centralized. The second one, by the way, was mass production and pipelining, but here the third one is rather exactly the opposite of centralization, where there's a new phenomenon, or rather new phenomenon at least, that every computer in every house becomes a small factory. And of course, what I'm talking about is additive manufacturing. Additive manufacturing means that in order to produce an object, we, as you can see here, if you want to produce this hemisphere, then we, layer by layer, we add material in order to produce it physically. And this is, of course, in contrast to most traditional manufacturing processes, which are more subtractive, where you drill into a cube of material in order to get your object. And this is, of course, what we call 3D printing, and the term 3D printing was actually coined at MIT in 1995. And this manufacturing process that I want to talk to you about, which I'm sure most of you have heard about it at least, is really radically different in approach, in concept. And we can really see that along throughout last years, we see a lot of attention from the media, from the academia, funding agencies, whatever, regarding 3D printing and additive manufacturing, and really saying, and they all say that this could, as you can see here, change the world, or it's very disruptive in the world of manufacturing. And it has already been used in many applications, starting from memorabilia in art, through fashion and gadgets around the house, and even medicine. And we'll talk about all of that in a bit more details along this talk. But first, I want to ask why. What's the big difference about 3D printing or additive manufacturing compared to traditional modes of production? And there are three very main advantages to this technology. The first one is there is less material waste, right? As I said, usually what we do is we take a block, let's say using CNC. You take a block of material and you start drilling into it. There's a lot of material that goes to waste in chips and residue and whatnot. And with additive manufacturing, there's also almost no waste. You use the material to build up your object. The second one is shipping costs. And you could say that additive manufacturing, and we'll discuss this a bit more later as well, allows a lot less assembly, allows generating more complex geometries and objects, and therefore we can produce one part that's very elaborate instead of having a lot of them and combining them and assembling and using it through assembly. And even more than that, imagine that at least the paradigm nowadays is that a customer, let's say in the US, requires or orders a product. It is manufactured someplace around the world completely. It could be on the other half of the world. And it's not only produced there, it's produced in 3 different factories there, and then it's shipped to a 4th factory to be assembled, and only then is it shipped back to the US for the customer. This process takes time, it takes a lot of energy, and there's a lot of shipping involved. And with this new paradigm of additive manufacturing, everybody's talking about, or analysts are predicting, that we'll have factories or a line of these machines that produce, top to bottom, produce objects that are very close to the customer. And this means that there's going to be a lot less shipping. You don't need to send stuff around the world just because it's easier or because manpower is easier somewhere around the world. And it's also faster. There's more the faster turnaround time for the customer. And I think the last advantage, where everything else is more or less taken from, derived from, is the complexity. The main advantage, I think, in my opinion, that computational fabrication or additive manufacturing offers us is being able to generate an object with basically an arbitrary amount of details without it imposing any additional cost in the production process. This is, of course, in sharp contrast to subtractive manufacturing, where every detail that you would like to add, you need to drill and actually, or mill or whatever, to create it. And here is an example. Here we can see an example of a cube that is more or less 10% of its original weight, but is just as strong in specific load directions. And of course, you can imagine that such a cube is really impossible to generate using traditional methods. And really, if you think about it, you could say that what the manufacturing world is undergoing is actually very similar to what the printing world, the 2D printing world, underwent only a few decades ago, right? Only a few decades ago, every single printed material out there was produced by a handful of people that had access to these huge press machines. And nowadays, we all have printers in our homes, and we can, print a form to take with us and then throw away 10 minutes later, or a coloring sheet for our children, on a whim. And the same thing is happening now with physical objects being manufactured. Up until now, everything manufactured around the world was, produced by the people that had access to factories, to huge manufacturing machines or milling machines. And now we see this trend where we have more desktop factories, we have more desktop 3D printers that everybody can use. And indeed, we see communities like Thingiverse and Shapeways, communities of people sharing models, sharing designs, and producing them at home, and really creating, like hobbyists, makers, communities that are growing in numbers in unbelievable tens of thousands of people. Right, and I want to say here for a sec that, even today, books are still not printed at home, right? You still buy them at the shop, and they're being manufactured in a mass production printer. The same thing will still be true even in, a few years, or in a decade. I expect the same thing would still be true for 3D printing. We'll still buy our couches at the store, and we'll still need carboners, we'll still need all of these. But on the other hand, we might not need spare parts anymore, right? We'll need less storage, and we might not even have screws, which are a generic form of connecting or fixation between two geometries, because we will be able to produce the exact geometry that we want that might be able to interlock into something. Or if we broke a level on our ladder, then we'll just be able to produce it and connect it back without needing to keep at home any part over a long period of time. Or maybe not even at home, even the manufacturing process, the company that made the ladder doesn't need to keep storage units full of replacement parts. They can generate it on demand. So I think this is indeed a significant revolution that should not be ignored. So what I want to talk to you today about in this talk are the following. First, what is additive manufacturing? I'll show you a few of the technologies out there and what it means in general. Then I'll talk about what the challenges are, and of course there are still many, for this field. And finally, I will talk about maybe the question that you all have at this moment. So, what does it have to do with me, right? What is computational fabrication and 3D printing has to do with the graphics and specifically the geometry processing community? So, I'll try to answer this question, and then, time permitting, whatever we'll have left, I will talk and show, just demonstrate a few examples of what has been done in the graphics community in the context of computational fabrication. And what I hope to achieve from this talk is that you will understand this term that is called fabrication-aware design. And this is where graphics and geometry will come in, where we help design the objects better to be printed. Okay, so this is a list, or this is the formal list of technologies that are recognized as additive manufacturing technologies or 3D printing technologies. I will go through the main of these, and then I'll talk about a few that are not in this list but are emerging and getting more and more traction. So the first one is what we call FDM, Fluid Deposition Modeling. This is the most common technology that is used for additive manufacturing in households, in low to mid-end machines, and end users that are not professionals will most probably meet this technology the most. And the idea is very simple. We have a spool of, or it's just a long wire of plastic, and it is being pulled down or pushed down using this extruder. So this is the spool, this long wire that is rolled up. It's called the filament spool, and this plastic is a polymer usually, and it is being pushed down. Here you can see that it's using like a cogwheel. It's being pushed down into the nozzle, and the nozzle has a heater that melts the plastic down, and then there's an extruder head, there's a nozzle that the liquid plastic comes out of. And then when you put the plastic down, it cools in the surrounding and the environment, and then it becomes solidified. It solidifies, it becomes solid. And then you can put another droplet of plastic on it. And that's the whole idea. So here is an example. Here we have a head. You can see this is the extruder and the head, and at the end it's this nozzle, and it's moving left, right, and forward and backwards. Sorry, it's only moving left, right, and we have the tray. The tray is where you deposit the material on, and as you can see, this tray moves backward and forwards, and layer by layer, the head here goes also upwards. Layer by layer, we have our object being formed. Of course, this is not the only configuration you can see. There are many cases, most cases actually, the head goes left, right, and forward and backwards, and then the tray only goes down. All right. Another technology which is very common, and I think is becoming even more popular lately for end users and low to mid-end machines is, well, I combine them, but they're very similar, SLA and DLP, or stereolithography, and digital light projectors. Let's look at DLP for a sec. And the idea here is that we have material that is solidified not using thermal dynamics, right? Not by melting it and having it cool down, but it's solidified using light. So we have a resin that is light sensitive, and we have an actual projector underneath the machine, and using light, it solidifies a layer. And then we have the tray now goes up instead of going down, and it solidifies another layer using another pattern that's being projected. And as you can see, because this is not, or this is less mechanical, we can achieve very, very high resolution details using this technology. And that's why I think it's getting more traction lately. As you can see, that's a coin, and you can get the scale here of the details that you can generate. And these are all home level machines, desktop machines that are very affordable. The third, I think, most important technology is laser melting, laser sintering, or laser melting. And the idea here is that we have lasers that heat up a powder or a chip or a bath of very small particles that the laser melts into a layer of what we want. As you can see here, we have usually it's a few lasers that combined into a single point, and this point fuses, sinters, melts, whatever the verb you want, and it depends on the technology, um, generates the layer through melting together these chips, this bath of powder. And usually, right, so here we can see usually that the biggest advantage of this technology is that this bath of chips can be metal. And there are a lot of metal SLS printers, and it can also be some plastic with nylon, but I think this is the biggest advantage. It generates metal parts that are really strong, and they are as strong as parts that are generated in another manufacturing process. Here again, you can achieve rather high detail level and resolution, as you can see, and it's being used for art and as well as for functionality that we'll see a few examples of later. Another technology that I think is important to be talking about is plaster-based 3D printing or binding-based 3D printing. And the idea here again is you have a bath of powder, but this time this powder is plastic, and instead of melting it, you just glue it. So you have a head that is more like an inkjet printer that ejects or jets a glue, and it binds the powder together to form the objects. And the nice thing about this technology is that this glue can be mixed with pigments, and you can get full colored objects after you clean the powder off them. Of course, there are many problems with this technology because, well, the granularity, the resolution that you can get to depends on the size of the grains, and this is still, very chemical process that is as strong as the binder, and so it's not. These are usually not very strong parts, and I think personally that I see less of these technologies lately. These printers are losing their popularity in favor of other ones. But still, this could you can find this in professional high-end machines. This approach, and the last technique I want to talk to you about, or technology that I want to talk to you about, is photopolymer phase changing jets. So the idea here is that very similar to what we said before, we have a pool of material that we deposit onto the tray, but this material is a light sensitive polymer that solidifies through UV light and not through the air or through visible light that we've seen before at the DLPs. And here is an example. And the nice thing here is that you can mix the materials as they are liquid. If you have several types of materials, you can mix them while they're liquid and then deposit them together to achieve a mixture of their properties. And you can have, it's very easy to have several cubes that go into the machine, and then you can have several materials being printed together at the same time. And here is an example of, fast forward or time lapse of such a print. As you can see, there is a white material and there's a black material. There's also support material that we'll talk about later. But here is a combination of the white material that is very stiff in this example and the black material that is rather flexible, and together we achieve, sorry about this, and together it achieves a part like this, which can be moved and pressed, and it's like a remote control. Yeah, you need to wash away, but this is the part that you get. Right, and the biggest advantage here, and this I think I would say, again, in my personal opinion, is one of the most popular technologies for higher end machines, professional, large scale, room size, or almost room size printing machines. You will use this technology. And one of the biggest advantages of this technology is that because it doesn't require heating, and it cannot burn when when overheating through the nozzle. It's easier to control, therefore you can achieve higher resolutions using these technologies. And even more so, there are a lot of materials. I think these technologies have the highest variety of materials that you can use um, during your prints. And this is everything from rather strong materials to temperature resilient materials to various optical properties such as transparency, different colors, opacity, and also different physical materials such as something that's more flexible, something that's stronger, can be stretched a bit, and also we have biocompatible materials, and these are actually materials, and these technologies are actually being used to generate um, cameras that you can swallow to that film your digestive system from the inside, and other types of pills and all sorts of stuff like that, and implants, and these all use these medical or biocompatible materials. And of course, here are a few examples that you can do using these technologies. Here is a wheel that, again, the white material is more stiff and the black material is more flexible, and you can actually, it comes out of the printer like that, no assembly is required. You can use it, it works, it rotates, it's a wheel. Here again is a combination of a soft and hard material to generate a brush. You can use the transparent material for educational purposes, and of course art. Here is a hearing aid. By the way, just for as a general knowledge, something like 98% of all hearing aids nowadays are printed, and in the world, and when you and the newly manufactured ones, all of them, 100% of them, are 3D printed, and this is because 3D printing offers a lot of flexibility. You don't need to really form a pipeline, a manufacturing line that or molds for very specific shapes. Every shape can be different, and therefore everything that needs customization actually adheres towards 3D printing technologies. So these are the technologies, but of course there are a lot more. For example, food is nowadays also being printed, and there's a chain of restaurants that every dish that they serve has at least one element that's actually 3D printed. The kitchen looks like basically a line of machines. You can use 3D pens, right? So this is freehand. I wouldn't call it 3D printing, but it's definitely additive manufacturing. Um, freehand generation of 3D objects, as you can see here. We have concrete being 3D printed, and there's a very, I would say, beautiful project nowadays that really can that set up houses at less fortunate regions. As you can see here, this is a person, right? So this is a full-scale house with a very large gantry 3D printed based machine that extrudes basically like FDM, but extrudes cement instead of plastic. And as I was saying, this is being used in regions that are less fortunate to really set up houses in 24 hours for a house. So a lot of interesting things are being used for construction in 3D printing. Very lately we have 3D glass printing, which is also very interesting. So you have an extruder, an FDM style technology that just works in a very very hot oven, and then the glass melts and you can 3D print it into shapes. Let me lose the laser pointing here for a sec. I think we have a few, yeah, you can see here the objects that have been 3D printed. We can 3D print ceramics nowadays, and again the idea is that we use clay, and the clay is being printed, and then it needs to be heated into ceramics, and then you can see it here, right? This is again this is actually can be used with usual FDM printers when you change the nozzle. Yeah, so and then you put it in the oven, it becomes ceramics, and you can paint on it and everything else you know about ceramics. And there's also composite materials. So the idea is that if you don't want to print in metal, which is A, expensive, and B, it's actually rather cumbersome. You need to know what you're doing engineering wise. You need to be able to handle it well. So the idea here is to have very strong parts, 20 times as strong parts as usual plastic prints, and but the idea, and they're still plastic, but the idea is that they are reinforced with fibers, and the fibers are, we've seen it earlier here. Um, where is it? Right here, I think. Yeah, and the fibers are being embedded during the print, right? So this is the yellow lines that we can see here. There was, right? Where is it? Yeah, here. You can see these yellow lines, and these are fibers. They could be Kevlar, they could be hydrocarbon, they could be fiberglass, it doesn't matter. But we embed these fibers while during the printing process, and then they're really just cut and just lay there, and you cover them with more plastic and they adhere. Yeah, this is Mark Forge. They basically are the ones that introduced the first desktop affordable fiber 3D printing machine. And these prints, they are plastic prints. They're not a lot more expensive. They are as easy to print as plastic, but they are, as I said, more than 20 times stronger. Here you can actually see where a 3D printed piece, which is a plastic piece reinforced with fibers, is being connected to chains to actually lift a truck. Again, we missed it. It was right here. Sorry about that. They're here. Somewhere. What's going on? Something's wrong with the playback. But anyway, you understand the point. Alright, so these are the technologies, and now maybe we spend a few minutes in talking about what is it used for. So it's used in many fields. And here's the list. I'll go over a few of them, but I think maybe the most popular use is jewelry and home products of various flavors. It's used for medical industries. As I said, hearing aids, all of them are printed nowadays. You can print crowns and other dental implants and aids for implanting procedures. I have a 3D printed tooth on my own, very proud of it. Prosthetics, they are strong, they are easy, they are customized, they fit the person exactly. And implants for the same thing. There are also, as I said, other examples such as surgery guides. So you 3D print something that guides the knife or your tool to the very exact place you need to perform the operation. And this is again patient customized. So very interesting uses in the medical arena. Footwear, there are actually lines, like here is an Adidas example. There are actually lines of shoes that are being 3D printed because they have soles that are very, very, very tuned and calibrated for specific responses to specific loads. You can run with it. You can do you can maneuver with it very easily. And these are high-end shoes. Some of them are really also customized to the athlete using them. Some of them are more generic, but still these are high-end shoes that their soles geometry is so complicated that it has to be 3D printed in order for it to be feasible, right? So the 3D printing technology actually makes the manufacturing cheaper there, and this is due only to the fact that the geometry is so complex. Of course, you can use these new novel geometries and a lot of details also for more fashion uses and less for functionality. But of course, both of them together are great. In architecture, this is also used. You can use this, of course, for prototyping, for generating the models easily when they're in smaller scale. But here, this is from MIT's entrance to the computer science building. But you can also use them to 3D print molds into which you pour the cement, and then you get bricks that are every brick here is different, more or less, right? So you can have customized bricks that can be used, and this reduces the cost of special manufacturing, customized manufacturing. It reduces the cost significantly because the molds are a very significant part of the cost for that. Actually, there are works also in geometry processing and in architecture. There are works that, given a building or a shape that needs to be generated using bricks. There are works that work on minimizing the number of molds you need in order to generate a building, or in other words, you want to find as little as possible different options for bricks that together with only these types of bricks you can generate the shape that you're looking at. So again, so 3D printing actually alleviates this problem and makes the customized bricks process a lot cheaper. In aerospace, this is again being used. Here is a wing bracket used by Airbus. This piece and others like it are being used all the time in engines and all sorts of very complex machineries, because of the assembly thing that we talked about earlier. So, for example, in an engine, there is a piece that is 3D printed on the mass production line. One piece is being 3D printed because it replaces 21 other pieces that needed to be assembled together. And taking this a step further is the wing structure. Now, this is still doesn't exist as far as I know for available planes and consumer level planes, but there's a lot of work going into designing now wings and hulls of planes to be very sparse and have this very involved geometry, because like the cube I showed you at the beginning, if we can make this a lot more light and yet as strong as the solid version counterpart of it in specific directions where the stress will be, we can have we can save a lot of energy. Think about if you had a plane that its hull is a third of its original weight, and yet it is as strong. It will save fuel, it will save material. There's a lot of advantages here, and I really think that we will see 3D printed hulls of planes or wings at least in the coming future, in the near future. The same goes for the automotive industry. Here on the left we can see even a tire that is it's natural structure inspired, but nonetheless it is 3D printed using rubber, and there's no need for air. There's no flat tires in such a tire. Right. And of course, as I said, home products, being it functional or just beautiful, there's a very wide variety of and a lot of creativity that goes into these types of creations. Now, generally speaking, this is not only, I just wanted to give you these numbers just to give you a sense of how big this industry is. I think it's still very small. It's according to, again, analysts and reports. In 2019, it was around $10 billion, the amount of products or ware that was produced or sold using 3D printing. But as again, in 10 years' time, this is expected to be 5 times that it is today, and actually maybe be a significant part, a non-negligible part of worldwide production. And this worldwide production has already been shown, at least in theory, in research. It's already been shown to save global energy. We've talked about saving global shipment costs and pollution emission that comes along with it. So there's a lot of things to anticipate to. As I said, I also expect it to really change the way we think about consumption nowadays. As I said, there's no need for buying a bag of 1,000 screws. You can generate the screws you need on the spot, and the sorts. Okay, so additive manufacturing is great, right? I've talked about all the advantages it has and all the potential it has to change our future in positive directions. But maybe we should talk a bit about the challenges and what doesn't work for this technology. So I want to divided it into two regions or classes. And the first one is the hardware challenges, which is not our community. And if we talk about mechanical and electrical engineering challenges, then prints are still very slow, and this could definitely be improved. They're rather expensive, and the print volumes are also pretty small. Okay, as I said, I'm excluding from this the building, the construction 3D printing, cement 3D printing, but all other 3D printers are really rather small. And if you think about it, if you have a motor and an extruder, it can potentially just move anywhere in a large volume, but still there are engineering challenges in order to make that happen. So there are, as I said, room size machines, but they're very, very expensive and very few of them. So these are still challenges that have to be met in order to make 3D printing more, I would say, accessible, right, and popular. Um, Another aspect is material challenges. So we still don't have the span of materials for 3D printing that we would like. Um, we would like to have more transparent materials, more opaque materials, a more variety of colors. We want to have better control over physical properties, stronger materials, lighter materials, more stretchable materials, materials that have specific magnetism or connectivity properties. This is almost untapped at all. Heat transfer, heat resistance, all of these, they're still very limited when talking about the variety of materials that you can 3D print with nowadays. Another point is the interface between materials. A lot of 3D printed materials that are multi-material break the interface. These are the weakest points. So again, this is something that needs to be worked on, and all of these are in the material sciences regimes. In software challenges, I again, this is my observation or my interpretation of the field. I think there are three main challenges or three main problems that need to be overcome, and these are complexity, complexity, and complexity. And the first type of complexity is complexity in the design space. Here is an example, right, of a car, of a hull of a car that could be 3D printed. And as you can see, the intricate or how involved the details are is a lot more than usual, rods and screws and steel bars that constitute a regular hull. The design space is a lot larger. There are a lot more options of what we can do now, and we don't have software tools to handle this. And I'll talk about this more in the coming minutes. But think about the amount of options you can have now for basically the same cost of manufacturing. And there's no way that a human could have, designed such a structure to be strong and very lightweight. And therefore, we need to have a lot more optimization in the loop, a lot more automatic operations that adhere to specific specifications, to specific goals or objectives that we want the part to have, rather than actually controlling the geometry. So this is still a lot of work to be done here on the right optimizations to generate these intricate parts. And another challenge that I think is equally important is the design interfaces, the design tools. So design tools nowadays, even the simple ones like Google SketchUp, assume that if I didn't say anything else, the material is solid, or there are no extra details, and there's a smooth interpolation between 2 points that I touched. Of course, this is not relevant anymore to the 3D printing paradigm. And as I said before, we should have more optimization in the loop, and we should be able to let designers dictate what we want from the piece rather than the exact geometry it has at every point. And of course, this becomes even more challenging for professional CAD tools or design tools such as SolidWorks, where the learning curve is really really steep before you can use this effectively. And if we want to transition to a paradigm where, okay, we have the experts, and for the experts there's still a lot of help that needs to be done in the optimization part, but if you want to have a 3D printer, or in order for this vision to come to life, and have a 3D printer at every desktop or every few houses at least, um, it has to be a lot more accessible. And this is, and nowadays design tools. I don't know if you have any experience with trying to design an object as simple as you can think of. If you've tried that, you know that it's really, really, really not intuitive and not accessible for everyday person. And lastly, the last okay, I'm sorry, I'm missing a slide, but the last a challenge is the one of representation. Now, again, think about, if we look at the example from here, if we think about this and the printer level, every voxel, right, every little piece in the volume, in space, at printer resolution could be different. There could be a droplet of material there, or there maybe isn't. And if you want to be able to really exploit the full power of 3D printing has to offer, we really could at the resolution, at the printer resolution level, decide for every voxel what material should be in there. But this gives us teravoxels for a cubed foot, a single foot. And so as you can think, I mean, imagine trying to design this car. The amount of information you'll need in the space and on the file system that you'll need only to store something like this in its full resolution is unbearable. And then what if you need to run a physical simulation over this huge amount of information, right? It becomes infeasible. And then what if you want to run an optimization that changes the geometry and runs physical simulation every iteration? This is completely unfathomed. So there's a lot of work that still need to be done in the space of how to represent these very very complex geometries. Okay. Um, ah, yeah. Sorry. Here is the. I'm sorry. Here is the exactly the drawings that I was talking about. So imagine trying to optimize this piano to form a specific sound, but everything is stored at the voxel level. This is, as I said, teravoxels for a cubed foot. This is not completely unfeasible. For the metric system, this is about 300 megavoxels for a cubed centimeter. Right? These numbers are completely unthought of. And I want to say one more thing here. We've seen in the past, and I think, as I said, in order for this to come to life, this vision of globally saving energy and saving transportation and emission and pollution and all that, and material usage, in order to do that, the software has to be able to easily exploit the capabilities of the hardware. And we've seen this in the past, right? We've had a in the past, in the early late 80s, mid 80s, we've had these machines, these Macintosh machines, and the PC machines that emerged at the same time, and were similar in performance, but according at least to some, the Macintosh performance was more significant, or superior, and yet we, for many many years after this rivalry, we had the PC market was dominating the Apple one, and this is because of, at least according to some analysts, this is because of the software that came out. This is what now we call Excel or worksheets or digital sheets in general, but software came out that exploited the PC better than the Mac and therefore the sales of the hardware, even though the hardware was inferior, the sales went up drastically, and this is what we call the killer app, right? This is a term we use until today, and and yeah, the only thing that saved, basically, again, according to some analysts, the only thing that saved the company back then from bankrupting is because they came out with their own software advantage, which was what you see is what you get approach, where printing came out very similar to what you could see on screen. So these machines became more popular for graphical applications and communities. And yeah, so again, for these communities, the killer app made a difference. So I'm claiming that the same thing is happening now. We have 3D printers that can do a lot of interesting and intricate geometries, but we don't have the right software to support it. And this is where we come in and we have to help. Okay, so the next part of my talk is going to be about the connection between graphics and geometry processing to computational fabrication. Now, when you think about, okay, how can graphics help computational fabrication, I guess the first thing you think about would be, well, appearance. And indeed, through this type of work, I would say, was how the connection was made between 3D printing and graphics. And I would also claim that, at least for design tools, graphics community is the one that's leading the front for the fabrication field. So here's an example of a work that came out also already 6 years ago, and it took advantage of things that we knew for decades in the graphics community and the image processing community, where we used to have screens that could only display black and white, and we had techniques like halftoning and dithering to form different shades of gray. And here we have now all of a sudden these machines that can print only using two materials, right, in order to generate objects. And it could be only black and white, but we want to have shades of gray, or we want to have details. And here is an example that uses halftoning in order to improve the visible appearance quality of 3D printed parts according to requested targets. This, of course, came even. This was evolving and evolved into this, and this is still evolving. There are still works. Even last year, work still came out that addressed this problem. And here is another example of these works from a year later, where rendering, or our graphics understanding of how light behaves, helped in deciding which color to put at every point, because these materials, as I said, they're not completely opaque, and light comes into one and comes out of the other, and visually you get blurriness of details. So this work learned how to, or proposed a method that compensates for this blurriness to generate much sharper, as you can see here in the zoomed in image, much sharper appearances for printed parts, even though the materials are semi-transparent. And there's a lot more work that takes advantage of various optical phenomena, BRDFs, shadowing, shading, caustics. All of these effects, optical effects, have been exploited in generating actual 3D parts, and more works along these fields come out every day, every year. But the story doesn't end with appearance. It starts with appearance. Yeah, graphics are good, with optical, with understanding of how light behaves. And this was sort of an opening to the field of 3D printing, but there's still a lot more. For example, physical simulation. I mean, physical simulation is not something graphics invented, of course, but there's a very significant difference, I would say, between physical simulation and physically based simulation, which is what we do in graphics. So with the computational sciences, it's very important to reproduce physical phenomena, right? We need to know exactly how much traction the air will have with the car in order to know how much fuel it's going to use, and we need to have very, very good understanding of the forces in the the driver's seat has when crashing. Otherwise, will generate a non-safe car. But when talking about graphics, um, it's more about imitating physical phenomena and having this faster and these simulations having them faster and more controllable and more stable rather than being more accurate. And as it turns out, these simulations are nowadays accurate enough even for the needs of 3D printing, and because we are faster and more controllable, we use the knowledge that came out of the graphics community can be used in optimizations for the field or for objects to be printed in a much more efficient way. And as we'll see, and I'll discuss now and show a few examples, this actually opened the door for a lot of applications that were not dreamed of beforehand. Here are a few of examples of what we know and what we can do in graphics for physical simulation. So here's an example for a fluid simulation where the size of the particles are adaptive to the amount of details required in that region. We are very good also with rigid body interaction, right? So here's an example of, this was a project in a course ITA'd. This scene is made of tens of thousands of wood planks, coupler planks. And as you can see, now it's being bombarded by pasta and meatballs. But this is a very, very elaborate scene with a lot of numerical problems, and setbacks pitfalls that could make this simulation explode totally and not look realistic at all. And yet everything collapses here. Nothing is glued, right? Everything just lays on top of each other, and still we are able to perform such accurate and efficient simulations. Of course, other things like fracture and sound, there's actually a very interesting work that I won't have time to go over, but a very interesting work that generates 3D prints objects that make specific sound if you blow through them. And maybe the most important part is elasticity. Again, this is just an example of work from graphics, but we use mechanical traditional tools like FEM and approximations for rods and shells. We use these techniques in graphics works in order to make more accurate, faster, more controllable physical simulation that can be exploited for 3D printing. Here's an example of one of the such works. Here we have a target shape, so we want to 3D print this plant. But if we 3D print this geometry, the desired geometry, when gravity is applied on it, then we have a deformation, right? And it's not the shape that we would like to have. So what this work has done is compute what the initial shape should be, such that after you apply gravity onto it, you get the desired configuration or the desired shape. And not only that, it doesn't have to be gravity. It could be any sort of load that you specify to it, and then a 3D print is computed, or 3D shape is computed in order for it to be printed to imitate these required shapes. Here is again, and it doesn't have to be only one shape, it could be two. Right, so here the desired shape is that without loads and another one with, and here we have 4 different shapes with 4 different loads, and one object is printed such that when you give it this load, it will match this shape. Right, and of course the last and maybe most relevant topic in graphics that is relevant to computational fabrication is geometry processing. And let me go a few of the things that are relevant here. So first of all, maybe the most relevant part of geometry processing to computational fabrication is representations. As I said before, we cannot, it's simply unthinkable to represent a large-scale full design in its maximum, voxel printer resolution. it just becomes infeasible. You need whole hard disks just to save. So we have to come up with more, maybe hierarchical, maybe procedural, maybe even programmatic representations that tessellate the geometry on demand and doesn't save all the geometry throughout the whole thing all the time. So here is an example for a work that took advantage of octrees. Octrees, that's a hierarchical, representation or data structure that is able to unify together regions of less interest. So here, this work, what it did was basically merge together small voxels that were of the same properties, so of the same density, or with material, without material, void. And through this octree, using this octree, it was able to generate objects that have controllable center of mass and axis of momentum. So if you take something that's not symmetric and you try to rotate it, it doesn't work, right? It doesn't rotate because of the momentum is not at the right point. But if you hollow very specific parts of it, you get something that rotates exactly around above the point of contact with the ground. Now you could say, okay, well, this is already rather symmetric. It's almost symmetric. But what about more elaborate shapes, such as not this one, but such as this one? We take our armadillo. Everybody knows the armadillo, right? And again, this project is able to hollow it such that it still looks the same from the outside, but has a very specific physical property of having the axis of moment of rotation, exactly around above the specific point of contact with the ground. Here again is even a more elaborate example. Other representations that have already been used in various works in computational fabrication is the medial axis. The medial axis, if you don't know, it is a structure that looks at center lines. It represents in this case, a volumetric shape by a surface in the middle of the shape and offsets from it. So it represents the volume, but in a more efficient way. And this way reduces, one dimensionality, right? It goes from volumes to surfaces, and it can go from surfaces to lines, as you can see here. But you can still run your physical simulation over this, making this a lot more efficient. And this medial axis also is keen, and we know this from traditional geometry processing, is very good at representing the geometry or the semantics of the geometry, right? So in this case, what this work has done, and this is one of the seminal works in the field, it's already rather old, but still, what they did was identify weak regions and then either thicken them by enlarging the offset from the medial axis in specific places where they were weakest, or they also used the medial axis in order to decide what to connect or to add rods and supports in order to connect pieces together and making them stronger inside and outside. Another very, very useful representation that maybe could have a lot more potential is spectral decomposition. I think you will be talking about spectral decomposition in this course in the SGP graduate school, but I want to show you this example. So spectral decomposition is about, it's something like a Fourier decomposition, right? It's about representing the frequencies that when added up generate your object. And in this work, what they did was they said, well, I want to optimize my object to have specific physical quantities, such as the moment of rotation that we talked about earlier. But it could be also other things like flotation and then center of mass, and they have a few more examples. But in any case, what they say is, okay, so I want to generate this, optimize this shape in order to have my goal, but if I go and optimize every voxel or even every cell in the octree, there's many parameters. So instead, maybe what I should do is just control parameters that deform the lower frequencies of the shape. And that way, higher frequencies remain the same. All the details, all the intricacies, all the decorations, they're still all there. But the shape changes in the low frequency, deforms just a little bit, and this is something the human eye is less perceptive to, deforms just a little bit in order to generate, this nice physical phenomena. And here's an example. So what we do is we deform the bottle just a little bit if we need to, and we also control thickness again only at lower frequencies in order to get the physical phenomena required. And here what they do is they show that they printed two bottles that externally look exactly the same, but one of them is stable when filled with alcohol but falls when filled with water. And the other bottle is exactly the opposite. It will fall when filled with alcohol and is stable when filled with water. And their joke is that, well, you can take this bottle to a bar and see if you've been had when given an alcoholic drink, if it has enough alcoholic percentage in it. In other except for representations, there are other tools in geometry processing which are very relevant to the world of computational fabrication. And this is, for example, just curvature, salient pieces in understanding saliencies in shapes, looking at the curvature of shapes. And for example, here what they did was, this is a work that tries to pack a 3D printed object better. Now, why would you want to pack something? Well, you have two options basically, or two applications that they talked about. One is, well, what if the volume, this animal, the armadillo, is larger than the print volume you can use, or higher at least than the print volume. But if you break it down, then it can be printed together. And the other one is, well, you can pack it like that and ship it already to the customer once it's packed, broken down and packed, and then it can be assembled on the customer side. And in order to do that, if you don't want to ruin the visibility or the functionality of your piece, it is better to cut it at less salient places, right? At places that are either more hidden from the eye or already have some feature, some linear line-like feature that you can use to cut exactly the same place. So they used that exactly. They used curvature and said, well, we're going to cut at either very ambient occluded places or at high curvature regions in order to create the pieces on one hand, but not ruin its semantic functionality and aesthetic on the other. Another tool is vector fields. Vector fields are actually being used in construction a lot for support for self-supporting structures. This is something that uses vector fields in a very nice way. I won't go into exactly how, but again, if you're interested, I really recommend looking into it. It's a very elegant and nice method. But also to approximate shapes. So we look at principal directions of the object. So we know that here, for example, in the finger, there are two principal directions. One is along the finger, and the other one is along the tubular radius of the cylinder that constitutes our finger. And then once we have these directions at every point on the shape, a vector field is designed to match these directions as well as possible. And then a plank, a laser cutter, or you could do this, of course, with additive manufacturing as well, but planes are generated that when combined, when interlocked, approximate the original shape very well. As you can see here, right? The amount of material used here is, I think, in the order of single one-digit percentile of the entire volume, and yet this shape is approximated very, very well. We all understand what we're looking at. Right. The last one is animation, but I don't think I am gonna go into it. I don't. This is not in the focus of this talk, so I won't go into animation a lot. But what I wanted to say was what does happen nowadays, or happened in the last few years, in this field of computational fabrication in graphics. And this is exactly what we call, again, fabrication aware design. Right? This all falls under that, I would say, that umbrella, or that topic, because this is not regular design. These are all design tools, right? If I want to be able, what did we last see? If I want to be able to approximate a shape and generate it using, interlocking planes, then I'm gonna design these planes in order to work. But this design process has to be aware of what the application is and what the fabrication method is in order to better um, align the final shape or the final, design, manufacturing uh, instructions to the needs of the design. Okay, so here, very recently, or not very recently, 2 or 3 years ago, I've done a state of the art report on works that have been done for fabrication aware design, and we have divided all of these works into these 5 categories. And I just want to, in the time I have left, I just want to go over each one of them in order just to give you, a general understanding of what are the types of work that have been done in the graphics and geometry communities for the computational fabrication field. So the first type of work, as can be expected, has to do with appearance. This is actual behavior of light, like in this example, where what they did was they took an opaque material and transparent material and printed them together to generate really fiber optics sort of phenomena. So now when one generates or connects a projector to the bottom of this piece, the light is guided into the piece, and actually you can see the eyes moving in sorts. And here it goes one step further to really have a non-planar display. There's a projector connected to the back of this shape, and a lot of these fiber optics have been printed while or along with the generation of this shape. And now every pixel in the input plane has a mapping to a 3D position on the other side of the surface. Now, of course, you can, for now, you can see each and every pixel, and this is just because of resolution, printer resolution, and as resolutions grow, this could be made more and more interesting. And 3D displays could be generated. But this is when I talk about appearance, I don't only talk about behavior of light. I also talk about aesthetics and things like texture synthesis. This is something that, again, graphics and geometry communities are good at or experienced with. And here's an example where a set of exemplars are combined in order to make a shape that on one hand is aesthetic, right, using these exemplars, but on the other hand, the generation, the process, makes sure that the printed part is stable and printable. So nothing is floating, nothing will break, everything is strong enough. Some of these forms are even deformed just a bit in order to better adhere to the continuity requirements and strength desires that the user dictates. The second class of works is strength and motion. So in this particular work is something I like because it really uses almost no physical simulation. There's only one step of physical simulation in the beginning, and it only uses graphics tools in order to make a shape that is a lot lighter and not much weaker in specific directions and loads. And the idea here, what they did basically was they used the physical simulation in order to dictate densities of seeds of a Voronoi diagram. So we have a Voronoi diagram, right? So these are Voronoi diagrams. 3D Voronoi diagrams create cells, 3D polyhedra that the edges of these cells are equidistant from two seeds. So the more seeds you have, the smaller cells you'll get. And therefore, the more stress or the weaker the part, the region in the part is, the more seeds it will get and the smaller cells it will have and the stronger it will be. But regions that don't carry a lot of stress, that are not very weak, they're not prone to break, can have larger cells. And that was the idea here. Run a physical simulation, seed these, generate the seeds according to the density of the physical simulation, and then generate the cells from these seeds. And then there's one more step about wall thickness that happens in between, and you get this structure that is a lot less material, but is rather strong. Of course, this is again the first in the line of works, but I like this one specific because it really shows the benefits of graphics over just engineering, mechanical engineering in general. Another work is able to, using again a spectral decomposition or modal analysis, if you know it, use a spectral decomposition to identify regions that are potentially weaker. And regions that are potentially weaker, like here as you can see, weak region extraction, what they did basically was they did modal analysis or spectral decomposition, and from the spectral decomposition, it is well known that you can know vibration at given a vibration frequency, how much will a region move. And the idea is that if something moves along many vibrational frequencies, it's probably weaker. It's more prone to break when you apply any kind of load. And so weak regions are extracted, and then the physical simulation runs over only these regions. And then the physical simulation part is significantly faster, especially since this whole process doesn't know or doesn't need to know what the loads on these objects are. This is part of the process. You understand where the weak regions are. For these, you do some sort of testing in many different loads, and then you end up with this weakness map. And this work is again significant and notable because it really speeds up the process of finding weak regions up to 10,000 times in a specific example. And indeed, many works that came after this one actually use this as a starting point. So this was all around integrity and strength, and now I want to also talk about deformation behavior. So deformation behavior means when I apply a specific type of stress or load or pressure, I want to get a specific type of deformation. So here is one example where we have this shape, and then we say it's a very small shape. And then we say if we apply force like this, we want the flaps to go up. And here we have this neutral expression sort of emoji where when we compress it once, at one example we want it to smile, and the other example we want it to frown. And then what this work did was generate a library of microstructures that had specific deformation properties. And then if you want a specific macro level deformation, all you have to do is tile these different microstructures, these different cells, together in order to drive the macro deformation in the direction you want. So again, this is work that came out of graphics and geometry communities, and my interpretation is that it was possible to do here and not in other communities because the physical simulation that everything is the underlying of all of these optimizations was more efficient. Other cellular structures here, there are two more examples here, and here again we can see the use of Voronoi diagrams. Here this type of shapes are called open foams, right? You can see how these shapes resemble foams that you can press on. And here what the requirement was different strength, right? Different deformation behavior. So this, when applied with force, this part was expected not to deform at all, and the blue part was expected to be softer. And the way to do it was, again, to spread seeds of a Voronoi diagram along the object, and then just connect the cell along these cells along edges to create this foam that can be of arbitrary strength according to this density. And the nice thing here, there were a few more nice things about this work. It's streamlined and it's continuous. You can generate what we call a graded materials that have smooth transition between very stiff and very soft objects and so on and so forth. An example is this one that I don't think I'll go into in the interest of time, but what I think is the most exciting type of works that the graphics and geometry communities have contributed to this world of fabrication is what we called high-level design. As it turns out, we at our community is very good at abstracting away through optimization requirements or desires of the user, right? So we are very good at identifying what easy things or intuitive things for the user to specify in order to get to feed an optimization and get something that's more elaborate. So here's an example of aerodynamics, right? There's a small GUI here where a user designs a paper airplane, and then the system during the design process corrects the design itself in order to make it more aerodynamic. It makes it more symmetric. It will maybe prolong the wings a bit according to what is necessary. And again, we can get very elaborate, very diverse sets of airplanes that when you throw them and you try them out, you see that they fly very nicely. And then, of course, if you've done this manually, you'd have to be an expert in aerodynamics in order to properly estimate the flight pattern or the path of the airplane, and you'll have to really also be very experienced with designing such things to know what affects this aerodynamic better or worse. So again, I think this is a classic example for fabrication-aware design. This is a design tool that's very aware of what's going to be produced at the end, and it makes the production that is very elaborate and classically would require experts and a lot of time. So it makes it available for novices. So children can use this GUI in order to design their airplanes. Here is a very similar example that goes even one step further, and here a set of mechanical mechanisms are automatically produced that match the motion that is requested by the user only on the end effector here. So what happens here, I think I have it. I'll show more examples in a second. I don't have the examples here, sorry. But while the examples are running, I'll explain what's going on. A user comes and draws for the leg, given a mesh with joints and everything, the shape. A user comes and tells the leg what the path of the leg should be. And there's also an option to play with timing and all sorts of stuff like that. And then the system automatically optimizes what the set of cogwheels need to be in order to reproduce the requested curves as well as possible. And here again, there was need to assess the quality of the curve. And a lot of what happened here was, a lot of the work here was how to really properly quantify given two curves that they are similar or perceptually similar or not. And again, this is classic geometry processing tools for this sort of work. In this example, two geometries are given and automatically a connector between the two is generated. And as you can see here, sort of examples, a cup is connected to a desk, a gamepad to a chair, a can to a belt, and so on and so forth. And here again, several geometry processing principles were leveraged in order to make this work. Another class of works have to do with the optimization of the actual manufacturing process. I didn't give this any time during this talk, but there's a lot of things that also, even the actual the actual printing process has gained from our community, and this is everything from making the print more faster, or being able to having a large print, knowing where to cut it and how to connect it back for it to be stable again, through minimizing the use of support material, and so on and so forth. And here, this is an interesting example that I did want to talk about, the only example that I wanted to show. This example takes a low-end machine that's not very accurate, and basically what it did was add a feedback loop to it. This is more than that. This is an open source sort of printer that you can modify and change, but what I want to talk about specifically is this machine vision assisted platform. So the idea is that on the head that moves and prints, they added a camera to estimate the depth and to estimate the geometry of actually what has been printed in the last layer. Now, because this is a low-end, low-accuracy machine, then some droplets didn't land correctly, or a bit too much of the fluid came out, or the position of the head wasn't very accurate when the position happened. And what this vision layer does is it looks at the geometry and what actually happened in the print, and then it knows for the next layer how to compensate for it. And through that, they got very, very high quality accurate prints using very low cost hardware. So I think this is a very interesting example. Another type of work, so that's the only work from this type that I'm going to talk about. And another type of work which I find not sufficient really are general frameworks. Works that what they try to do is not solve a specific problem, but make the job easier for upcoming works to solve problems. So here's an example of a work that tried to imitate the rendering pipeline, the graphics pipeline, for the fabrication world. What they did was, just like we have shaders, programmable shaders on the graphics pipeline, then they try to have these red stages where you can program what to do and how to tessellate everything. And the idea here was that you get a shape, you tessellate it into voxels, and then you move maybe these voxels a bit, and you can do finishing better and color better, and then that's the voxelization stage, and then the volume stage, and then you can dither there. You can do some dithering, right? If you don't have the colors you want, then you can do what I showed you at the beginning, in order to get the desired colors and all sort of that. And everything is, the idea here is that everything is already in a single framework. Everything is implemented for you, and you can focus on the optimization and on design more than everything around it and the overhead. And even more importantly, it is easier if everything works over the same framework. Then it's easier to join two works together, make them work in cohesion. So here's an example of something that also has a specific deformation behavior and a specific texture, right? And you can compare to previous work more easily. So it's also better for researchers. But of course, there's a lot more. I haven't even started scratching the surface. There are works that there are puzzles that that they lock and can be taken apart only with a single piece. Burr puzzles that are automatically reproduced. Rubik cube sort of games that are automatically produced. Furniture that can be, again, using this interlocking principle, furniture that can be interlocked together and used without a single fixation tool, so without a single screw or nail, and even be reconfigured to be different types of furniture. There are walking robots that are designed using fabrication tools that have no sensing and are still balancing and are able to progress. There are telescopic structures that can open and close. There's a huge variety of works and a huge variety of tools for designing shapes that can be manufactured. Yeah, and that is it. That was my talk. What I wanted to do again was really just to lay the field out for you, because the assumption is, or my experience is, that a lot of people don't really know the field a lot. So this is not about teaching you new tools that can be used in the field of geometry, but rather to show you what the tools in the geometry processing community can offer to other regions or the fields, and specifically this field, which I find to be very, very closely related to geometry processing. I am a geometry processing person myself. So what does the future hold, and what does it has to do with us? What would be research, what I expect research to be in coming years? First of all, we need novel representations. We need better ways to represent geometry, intricate geometry, elaborate geometry, large scale, plane size geometry in printer level resolution. And I don't know what this will be yet, but it will probably be hierarchical in nature, and it will probably be something that maybe encodes, as I said earlier, the expectation, right, the spec of a region rather than the actual geometry of it, and then an optimization could tessellate it in real time, maybe something along these lines. I haven't even mentioned machine learning, right? There's a large collections, there's a lot of collections out there of already ready designs, and a lot of wisdom and a lot of thought have gone into them, and this has to be leveraged in coming years. This has to be leveraged better during the process of designing. So if I design something that is similar to something else that has already been designed, a system, a learning system could be able to do a lot of things. It could be able to suggest how to continue or how to alter my design. It could suggest to know already what the loads on a typical design like that can be. It could suggest what the manufacturing process should be, what materials or what machine should be used. A lot of these things will probably come in the near future. More objectives. Right now, as I showed you, the most of the objectives that we're using are strength, aesthetics a bit, and more or less that's it. But there's a lot more things that can be done, right? As I said, connectivity, conductivity, heat conductivity, electrical conductivity, aesthetics. Even we don't know if something is nice looking or not. We have a lot of heuristics about that, but it's not an actual objective that goes into the optimization. And I feel that if we had enough objectives, we could specify when one of the objectives could even be general geometric similarity to a ready design, an already existing design. But I feel that if we had a lot of objectives, one could really even have a design process through the objectives themselves and their weighting and their dictation, and really get a lot of very, very, very expressive designs that adhere to what we want to do without really touching geometry at all. I mean, the designer not touching the geometry at all. Yeah, I think this is it. This is what I had to say. I hope you have understood or have gotten a peek into what has been happening in this world, and see what your potential on affecting this world can be. And I'm happy to take your questions in the session that we'll have in a few days. Thank you.